Okay, so let's start off by reviewing some basic calculus. We have this f function which equals 2x squared plus 3, and we're going to look for the derivative. So f prime of x, what do? We take the exponent, multiply by the base, and then subtract 1 from the exponent, which is going to give us 4x, and any constants are just going to disappear. Okay, so let's do multivariable calculus. We have more than one variable, and we're going to be looking for the partial derivatives with respect to each variable. So the partial derivative of g with respect to x, what we do is we take the derivative of x and then treat y as if it were a constant. So this 2x cubed is just going to 2x squared is going to equal 4x. Now remember, we're treating y as a constant, so just imagine this is like 2x. Well, what's going to happen? The x is going to disappear, and we're just going to be left with y plus y. And this y cubed, we're going to treat it as a constant, and it's just going to disappear. Okay, let's do the same thing. So let's do the partial derivative of g with respect to y. This constant is going to disappear. The derivative of yx is just going to equal to x. And then we do 3y squared. Okay, so these are all the partial derivatives of g, and if we put them all into a list, what we're going to get is the gradient. So dg. Okay, so this is the gradient, and the gradient has a property that we're going to use, and it's the path of greatest descent, or the direction of greatest descent. So if we wanted to increase the output of this function g as fast as possible, we're going to move the x and the y variables in their respective directions. And conversely, if we want to minimize the output of g, what do? We take these partial derivatives and then go in the opposite direction. Okay, so let's see how that works. Here we have the code in Python. This is the function up there. Let's randomly initialize x and y. And with this function, we're going to get an output of 258. Okay, so now let's use what we know about the gradient to minimize this function, and we're going to use an algorithm called gradient descent. And what that is we take the output of our function, it's called g. We're going to take our partial derivatives that we got up here, and then we're going to update the x and y in that direction, in the negative direction. And let's introduce a variable, the learning rate, and this is going to help us with gradient descent. So x will be moved in this direction. And you can see we start at 256. We're going to run it 200 times, and it's going to be minimized. Okay, so that's gradient descent. Okay, so we're going to take what we just learned in gradient descent and apply it to machine learning. And we're going to start it off with a very simple linear regression problem. And what that basically is we have our data here in the blue, and we're going to try and create a line of best fit with this red hypothesis line. So let's go over a little bit of the code at first. So our data points, we're just going to grab some dummy data. We're not going to make anything. Our m, this is a variable we're going to use to the size of our data point. Learning rate, we're going to use that in our gradient descent. The slope and y-intercept, this is going to be the slope for the line, or hypothesis line right here. Now we're just going to randomly choose these two numbers. We're not going to guess or make any assumptions. We're going to let the algorithm decide that is. So I chose -5 and 3. And the function, or the formula for our hypothesis line, y equals mx plus b, we take in an x multiplied by the slope and then the y-intercept. Okay, so the first thing we need to do in order to get our line of best fit is determine how good or bad our line is doing. And we're going to do this by calculating the error or the loss or the cost, whatever you want to call it. In this case, we're going to use the mean squared error. So what is the mean squared error? We're going to, let's break it down. So to calculate the error, what we're going to do is take the real point, an x, plug it into our hypothesis line and get the hypothesis y, subtract those two values to find out how far apart they are. We're going to square it to get rid of any negative numbers. And we're going to do that same thing for every single point in our data. and then we're going to calculate the average. So we're going to sum them all up and divide it by the number of data we have. And that is our mean squared error. Very simple. If we look at it here, we're just going to put it up in a running total. We're going to plug in every single data point into our hypothesis. We're going to get a y value out. We're going to subtract it by the real value and then just square it. And at the end, we're going to take that running total and divide it by the number of data point we have, which is m. And it's going to give us a mean squared error of 90 in this case. So here this is 90, and it's not a very good score. But you can probably tell that because it's not very well. So now we have to see how do we minimize this mean squared error so it's very close to the line. Well, we're going to be using gradient descent like we did over here. So let's look at here. So we're going to take the exact same algorithm. So this function, it's going to become the mean squared error, the function we just calculated. Now we're going to take the partial derivative of every single one of our variables. In this case, it's going to be the slope and the y-intercept. So partial derivative with respect to the slope, partial derivative with respect to the y-intercept. And then we're going to update our variables. So the slope is going to change in the direction of our gradient descent. So we look at that here. Now, to calculate the partial derivatives, it's a little messy, I would say, or non-trivial, so I'm not going to go over it. I will link something in the description. It'll be a Medium article that goes through it. Mine's going to look a little different because I like this way because it has cleaner code, but the other way obviously works. But anyways, let's go back here. So we calculate the partial derivative with the slope, partial derivative with the y-intercept, and then we're just going to update the slope and the y-intercept, multiplying it by our learning rate to give us some kind of control over it. Now the training loop, very simple. We just keep running this apply gradients function. Okay, and I think we can maybe look at what it's going to look like. And there we go. So you see that when we're updating our slope is going to slowly start matching whatever it is the slope of the data, I guess you could say. And you can see we're getting a line of best fit. So that's really all there is to linear regression. If you want to look at the code and play around with it, you can look at what happens if you have a larger learning rate. It's going to converge a lot faster. If we have a smaller learning rate, it's going to go a little slower. Just like that. But anyways, that's a fundamental thing of machine learning and linear regression. And let's go on to more advanced stuff. Okay, so now what we're going to do is review some linear algebra that we're going to be using. Mainly matrix multiplication. So we have two matrices here, A and B. A has 4 rows, as you can see, and 3 columns. And matrix B has 3 rows and 5 columns. And if we want to look at the shape here, we have a 4 by 3 and a 3 by 5. Now, in order to multiply two matrices together, we need one important thing, and that is these two middle numbers have to be the exact same. So what we see here with 3 and 3. Otherwise, it won't work, won't compile. So let's run our NumPy matmul. Let's multiply these two matrices together, and voila, it's going to work. Now the shape of the output of this matrix multiplication is 4, 5. Now where does that come from? Well, it's the first number here and the last number here. So that's what all you need to remember right now for matrix multiplication. These two middle numbers are the same, and the output is going to equal the two outer numbers, if you want to think of it like that. So let's look at, say, what happens if matrix B has 2 rows. So let's turn this into a 2. What will happen? Well, we'll get an error because it won't work. And we see the error, size 2 is different from size 3. Okay, so let's look at like what would happen if you matrix multiply instead of A by B, B by A. Well, it won't work, right? Because, well, I guess it's 5. So it would be reverse. So it would be the two middle numbers in this case would be 5 and 4. Now, if we want to go backwards like that, what we can do is dot T, which kind of transposes it. So let's look at the shape once we do a dot T transpose. And it's going to work. Now, those two numbers have to be reversed, but let's see. Let's do B and A. Make sure it makes sense. Okay. So you see, once we transpose them, we flip the dimensions if you want us to think. And we get a 5 by 3 and 3 by 5, and then we can matrix multiply. So that's all we're going to be covering right now. Let's go back to calculus, and we're going to be reviewing the chain rule. So here's our problem. We have variables x, y, and z, and we have two functions. Q, which is equal to x plus y, and f, which is equal to q times z. And we're going to need to find all of the partial derivatives, x, y, and z, with respect to f. Okay, so let's start off with what we already know how to do, which is finding the partial derivatives of single functions. So let's start with q. So the partial derivative of q with respect to x, well, how do we do that? Well, we're going to treat y as a constant, and it's just going to disappear. And then we just need to find the derivative of x, which is going to equal 1. Okay, then we can do the same thing with dq dy. Basically the same thing, we're going to left with 1. Easy peasy. Okay, now let's move on to the next function. So this is df with respect to q. And we're going to treat q as a variable, z as the constant, and what we're going to get left with. So say we have a variable f equals 2x. What's the derivative? Well, this variable is just going to disappear, and we're going to left with a constant, which in this case is going to be z. And then vice versa with df dz, it's just going to equal q. Okay, so this is stuff we already know how to do. Now let's get on to the chain rule. So if we want to find the partial derivative of f with respect to x, how are we going to do that? Well, we're going to take the inside function and then multiply it by the outside function. Now, the inside function will be dx, dq, dx, and our outside function is going to be equal to the q variable, so this derivative. So the df, dx, what that's going to equal to, inside function, which is 1, multiplied by the outside, df, dq, which is equal to z. Okay, and then we can do the same thing with df, dy, and it's going to be 1 times z again. Okay, so that's a quick overview of chain rule. Very light, obviously, so just some intuition. Okay, so let's move on to neural nets. And the problem we're going to solve right here is classifying this kind of spiral thing. So what we're going to do is we're going to see, grab a piece of data, and we're going to try and guess, is it blue, yellow, or red, based on this pattern. So, and the reason we're going to use a neural net for this is because a lot of maybe traditional machine learning algorithms won't do a very good job. If you want to think of maybe like drawing a line to kind of separate this data, it's kind of hard to do. It's not going to do a very good job. And you think of maybe some clustering things, well, it's not going to do a very good job, right? And so we're going to use a neural net in this case. So first thing, here's our dummy data that we're going to grab, we're going to make. And here are all the variables we're going to need into our neural network. So let's go over a neural network. It's quite simple. Neural networks consist of different layers, and each layer is going to have 3 parts in its simple form. First thing we do is we matrix multiply whatever we're sending into the layer with a weight matrix that we create up here. We then add a bias to that to kind of maybe shift it around, and then we add a nonlinearity and the whole thing. So a nonlinearity is basically used to kind of mix up the data, and we're going to be using a ReLU in this case, which is the simple most common one you're going to see. And it basically says any negative number that we send in is going to be 0. Any positive number is going to stay exactly the same. So that is a layer of a neural network. Now we take this layer and then we're going to have the output of this layer as the input to our next layer here. And then we're going to do the exact same thing. We matrix multiply it with a weight matrix, add a bias, and then we're going to throw a nonlinearity or a activation function on top. In this case, we're going to be using a softmax function. So if we go back to our data right here, the neural network is going to output 3 guesses, and we want it to be a percentage of each guess. So the neural network can say, well, say data right here, well, I'm 70% sure it's blue, 10% sure it's yellow, or 20% sure, or whatever. And the softmax is going to take a number and kind of turn it into that percentage. Now, instead of percentage, it's going to be like 0.7 or 0.2 or whatever I said. And basically means they're all going to add up to 1. So that's all the softmax is going to do. And that is the output of our neural network. So, okay, just like in linear regression problem, we're going to get a loss function and try and minimize that. Now in linear regression, what we use is mean squared error. We're going to use a different one, cross entropy or negative log loss. But we do the same thing. We calculate the loss and we're trying to minimize it. So our neural network is going to give us our correct answer. And the way we're going to train this is by doing gradient descent. And it's just going to look like this thing we've seen before. We calculate the partial derivatives of all of our variables, multiply it by a learning rate, and then update the variable accordingly. So this should be all new. Now, how do we calculate these partial derivatives? Well, let's look at a layer. So we had our input, we multiply it by weight, add a bias, or something like that. So how are we going to calculate all the partial derivatives? Well, so if you want to look at maybe df dw, what's that going to equal? Well, we're going to treat the weight variable as a variable, everything else is a constant. So what's going to happen is b is going to disappear, this w is going to turn into 1, and then we're going to be left with just an x. And we see that the x, in this case, would be the hidden layer. Now, we're going to apply the chain rule to this and then multiply it by what came before that with its d-scores. And that's going to be our partial derivative of our weight matrix. And we do that for each bias and the hidden layer, or the x layer. And we keep going back, and then when we're multiplying, we multiply by the chain rule by whatever came before it or after it, order. And this process is called backpropagation, or something where we keep propagating backwards, applying the chain rule and multiplying it by whatever came before it. And that is basically a neural network.